So, in the last class we actually completed a table. So, the last column of the table is voltage across a valve. So, we took one of the valves, valve 1. So, if I look at the voltage across valve 1. So, we got the expressions for these voltage across valve 1 for all the 6 intervals. Okay. So, if you look at the expressions, there are 3 expressions. Either it is equal to EA minus EB, or it is equal to EA minus EC, or it is equal to 0. So, it is equal to EA minus EB in the first 2 intervals that we considered. So, this is for omega OT greater than alpha and less than alpha plus 120 degrees. Then it is equal to EA minus EC for omega OT greater than alpha plus 120 and less than alpha plus 240 degrees, and it is 0 for omega OT greater than alpha plus 240 degrees and less than alpha plus 360 degrees. So, the inference that one can get from the last column of the table that we have written in the last class is that we can actually find out, I mean this is actually the summary, what I have written now is just a summary of that last column. So, we can find out what is the magnitude of the voltage jump. So, there is a discontinuous voltage across valve 1 in general. So, the valves are subjected to dV by dt stress. Of course, there is a specific value which is the maximum that can be withstood by the thyristor valve. So, one should not exceed that. So, if I look at, I mean I will come to dV by dt later, the rate of change of voltage with time, but let us first see what is the magnitude of the voltage jump. Okay. So, what is the magnitude of the discontinuity? So, there are 3 voltage jumps. So, jump is just a discontinuity. Now, if I want to find the magnitude of this jump, so what I should do is, so I suppose the jump occurs, if you look at the expression for the voltage across valve 1, at alpha plus 120 there is a jump. So, it goes from EA minus EB to EA minus EC. So, to calculate the jump, I take the value just after alpha plus 120 and from that subtract the value just before alpha plus 120, that is all I do. Okay. So, what I do is I calculate the value of the expression just after alpha plus 120, that is EA minus EC. So, from this subtract EA minus EB, which is the expression just before alpha plus 120. So, I have to evaluate this quantity at omega OT equal to alpha plus 120. So, if I evaluate this at alpha plus 120, I get the magnitude of the jump. Okay. So, I know the expressions for EA, EB and EC. So, I will actually fix the expressions for EA, EB, EC. So, if you recall, we wrote the expressions in terms of the RMS value of line to line voltage. So, EA is root 2 by 3 V sin omega OT plus 150 degrees. Now, the purpose of choosing this 150 for the voltage EA is I mean for the sake of having the instant of natural conduction for valve 3 as 0, that is the only point, there is nothing more than that. Okay. So, one could have chosen any arbitrary value that. So, I just chosen 150 for the sake of taking one of the valves, say valve 3, the instant of natural conduction of which is 0. So, if I substitute the expressions for EA, EC and EB, what do I get? Of course, I mean I can substitute only for EB and EC because there is a simplification here, EA minus EA. So, it is EB minus EC. Okay. So, it is EB minus EC evaluated at omega OT equal to alpha plus 120. So, what is this EB minus EC? So, one can note that the expressions are like this. Let me write the expressions. EA is root 2 by 3 V sine omega OT plus 150 degrees. EB is root 2 by 3 V sine omega OT plus 30 degrees, and EC is root 2 by 3 V sine omega OT minus 90 degrees. So, given these expressions for EA, EB, EC, can I straight away say what is EB minus EC without doing any trigonometric manipulation? See, it is easy to visualize these voltages as phasors. So, if I take, say I want EB minus EC, so let me take EB. So, what is EB? The phasor EB is shown with an angle, phase angle 30 degrees. Okay. So, suppose I take the angle of the phasor as a phase angle in the of the instantaneous waveform. So, I just take the argument of the sine function minus omega OT. So, that gives the phase angle. So, that is taken as the angle of the complex EB. Then EC, what is EC? EC is having a phase angle minus 90. So, the complex EC is shown with an angle minus 90. Say all our reference, say all our phasors are with respect to the positive real axis. See, we do not explicitly show the real axis and the imaginary axis, but whenever we draw a phasor as a complex number, it is in the complex plane. Okay. So, what I mean to say is this angle is 30 degrees and this angle is 90 degrees. But what I want is EB minus EC. So, I should add minus EC to EB. So, minus EC is obtained from EC by rotating it by 180 degrees. So, this is minus EC. So, if I want EB minus EC, add EB and minus EC. So, complete this parallelogram, I get this. So, this is EB minus EC. So, I just use this convention of showing a complex number by an arrow over that. Okay. So, I have shown arrow over EB, EC, minus EC and EB minus EC. So, one can easily say what is the phase angle of EB minus EC. What is the phase angle? 60 degrees. And what is the peak value? So, peak value of EB is root 2 by 3 V. So, it is root 2 V. So, I can straight away write the expression, the instantaneous expression for EB minus EC as root 2 V sine omega OT plus some angle which is nothing but the phase angle of EB minus EC, which is 60 degrees. Now, what I am trying to point out here is, should I always draw this phasor diagram? I mean, with practice, many times you need not even draw the phasor diagram. Looking at the expression for EB and EC, I should be able to immediately or quickly write the expression for EB minus EC. So, that should be possible. See, the reason is all these are balanced voltages. So, if you take any of these EA, EB or EC, they are equal in magnitude and displaced by 120, due to which I can easily write the expression for the differences. See, the difference is in fact a line voltage. If EA, EB and EC are phase voltages, difference between any two is line voltage, and I can easily write the expression without even drawing this phasor diagram. Okay. So, this has to be calculated at omega t, omega OT equal to alpha plus 120 degrees. So, what is this? So, I get an expression for the first voltage jump as minus root 2 V sine alpha. So, this is the magnitude of the jump that occurs at alpha plus 120. So, there is one more jump at alpha plus 240 and one more at alpha plus 360. So, if I go to the next jump, the second voltage jump. See, we are talking about the voltage jumps across valve 1. Okay. So, if I look at any other valve, the waveform across a valve will not change with the valve. Of course, for all the valves the same waveform will be there, only thing is there will be a phase shift, that is all, except for the phase shift it is identical. So, the expression is 0 minus EA minus EC evaluated at alpha plus 240. So, it is EC minus EA. See, 0 minus of EA minus EC, that is EC minus EA. So, this is calculated at omega OT equal to alpha plus 240. So, should I draw again the phasor diagram to find the expression? So, I know the expression for instantaneous EC, I know the expression for instantaneous EA. So, EC minus EA will have a peak value root 2 V, and the expression is root 2 V sin omega OT plus a phase angle I should add. So, if EC is having a phase angle of minus 90, EA is having a phase angle of 150, minus EA will have a phase angle of, say I want minus EA. So, EA is having a phase angle of 150, so minus EA has a phase angle of shift by 180 degrees, minus 30, minus 30. So, EC is having minus 90, EA is having minus 30. So, a phasor of phase angle minus 90, another one is minus 30. So, the resultant is having a phase angle minus 60. So, this is minus 60 degrees. So, this is evaluated at omega OT equal to alpha plus 240 degrees. So, what is this? So, if I substitute for omega OT the value alpha plus 240, what do I get? I again get the same expression for the voltage jump as I got in the previous case, minus root 2 V sin alpha. Is that okay? Okay. Then there is one more jump. The third jump is happening at alpha itself. Alpha and alpha plus 360, I mean, they are displaced by just one cycle. So, at alpha itself. So, the expression is EA minus EB evaluated at alpha. So, EA minus EB. So, what is EA minus EB? Root 2 V sin omega OT plus a phase angle I have to add. So, EA is having a phase angle of 150, EB is having a phase angle of 30, means minus EB will have a phase angle of see EB is having a phase angle of 30, minus EB
210.
Yeah, better to get angles in between minus 180 and plus 180, minus 150. So, I have 150 and minus 150, not 0. My 150 and minus 150, the two phasors are 150 and minus 150, the resultant is minus 180 or plus 180. Okay. So, this is root 2 V sin omega OT plus or minus 180, does not make any difference. So, this is evaluated at omega OT equal to alpha. So, again I get the same expression for the voltage jump, minus root 2 V sin alpha. So, all the voltage jumps are having the same magnitude, in this case minus root 2 V sin alpha. There are 3 voltage jumps. Now, the question is, what is the stress dV by dt, the rate of change of voltage with respect to time? See, the point we are trying to consider here is what should be the rating of the thyristor valve as far as dV by dt is concerned. See, there is a voltage rating, there is a current rating, there is also a rate of change of voltage rating. So, the valve should be designed to withstand this dV by dt. Of course, the question is what is alpha. So, we have to take the value of alpha which gives the maximum possible maximum possible voltage jump. So, the maximum possible voltage jump you get if you take alpha is 90. Okay. Now, what is the value of dV by dt? Sorry, this is jump. See, this is voltage jump is just the change in voltage. What I want is the rate of change of voltage with respect to time. What is the value?
We will have to know the actual time, the practical time taken by association.
Yeah. Now, there is a small difficulty here. Now, what we have been assuming here is ideal device. So, in an ideal device, the time taken to go from one state to other, on to off state or off to on state is 0. So, this gives a value of infinity. But in practice, what we need to do is you take the transition time to go from one state to another, and that is common for all the jumps. So, the transition time is almost common for all the jumps. So, what we need to do is you have to divide these voltage jumps by the transition time. So, in practice, we have to take the time taken to go from the on state to off state or off state to on state, and then that comes in the denominator. What comes in the numerator is this voltage jump. So, that gives the value of dV by dt. Okay. So, that is how the magnitude of voltage jumps actually become important. So, one can say that dV by dt is proportional. It is okay. I will not use this symbol for proportional. It is proportional to the magnitude of voltage jumps. Now, it has to be noted that in practice, say otherwise if I just assume an ideal device, dV by dt will be infinity. So, in practice means I am not ignoring the time taken to go from on state to off state or off state to on state. Okay. So, the magnitude of voltage jumps gives me some idea of what will be the dV by dt, so that the valve has to be rated for the dV by dt. Okay. Now, we will look at the other columns of the table that we have written and try to get some more quantities. Okay. If this is clear, I will move on to the next quantity of interest.